The story of the Antikythera mechanism begins not with its creation, but with its rediscovery in the cold, shifting waters of the Mediterranean Sea at the dawn of the 20th century. In the spring of 1900, a group of sponge divers sheltering from a storm near the small Greek island of Antikythera descended beneath the surface and encountered the remains of an ancient shipwreck. What they found scattered across the seabed would eventually transform modern understanding of ancient technology. The wreck itself dated to the late 2nd or early 1st century BC, a period when the Mediterranean world was shaped by the cultural and intellectual legacy of Hellenistic Greece and the expanding influence of Rome. Among the cargo were bronze statues, marble sculptures, glassware, and luxury goods, objects that spoke of wealth, trade, and artistic achievement. Yet one object, initially overlooked, would prove to be the most remarkable of all. Recovered in fragments and heavily corroded, the Antikythera mechanism appeared at first glance to be little more than a lump of bronze and encrusted debris. It was only through careful examination in the years that followed that its true nature began to emerge. Embedded within the fragments were gears, finely cut, interlocking bronze wheels whose precision hinted at an unexpected level of mechanical sophistication. At the time of its discovery, no comparable device was known from antiquity. Ancient Greek engineering was well documented in texts describing water clocks, automata, and simple machines, but nothing suggested the existence of complex geared mechanisms capable of intricate calculation. For decades, the significance of the Antikythera fragments remained only partially understood. It was not until the mid-20th century that sustained scholarly attention began to reveal the mechanism's extraordinary purpose. Through X-ray imaging and detailed analysis, researchers uncovered a system of gears arranged in a compact structure, originally housed within a wooden case. The device, it became clear, was designed to model astronomical cycles with remarkable accuracy. The Antikythera mechanism is now widely regarded as an ancient analog computer. Its purpose was not merely to track time, but to predict celestial events, phases of the moon, solar and lunar eclipses, and the movements of known planets within the framework of Greek astronomy. It embodied a synthesis of mathematical theory, observational astronomy, and mechanical craftsmanship that was once thought unattainable in the ancient world. To understand the significance of this device, it is necessary to consider the intellectual environment in which it was created. By the Hellenistic period, Greek scholars had developed sophisticated models of the cosmos. Building upon earlier work by figures such as Eudoxus and Aristotle, astronomers sought to explain the motions of celestial bodies through geometric and mathematical systems. One of the most influential contributions came from Hipparchus of Nicaea, active in the 2nd century BC. Hipparchus is credited with developing trigonometry, compiling star catalogs, and identifying the precession of the equinoxes. His work on lunar and solar cycles, in particular, appears to have informed the design of the Antikythera mechanism. Although direct evidence linking Hipparchus to the device is lacking, many scholars consider it plausible that his theories, or those of his intellectual successors, were incorporated into its construction. The mechanism's complexity reflects a deep understanding of periodic astronomical phenomena. The gears encode cycles such as the Metonic cycle, a 19-year period after which lunar phases recur on the same dates of the solar year. This cycle was well known in antiquity and used to reconcile lunar and solar calendars. Another cycle represented within the mechanism is the Saros cycle, approximately 18 years long, which governs the repetition of eclipses. These cycles were not merely theoretical constructs. They had practical applications in calendar regulation, agriculture, and ritual observance. Accurate prediction of eclipses, while not essential for daily life, held significant cultural and philosophical importance. Eclipses were often interpreted as omens, and the ability to anticipate them may have carried both scientific and symbolic value. The Antikythera mechanism translates these abstract cycles into a physical form. When operated, likely by turning a hand crank, its gears would drive a series of dials on the front and back of the device. Each dial displayed information corresponding to a different astronomical cycle. Inscriptions etched onto the surfaces provided instructions and explanatory text, guiding the user in interpreting the results. The precision of the gearwork is particularly striking. The teeth were cut with a regularity that suggests careful planning and skilled execution. Some gears employed epicyclic arrangements, systems in which smaller gears rotate on larger ones, allowing for the modeling of non-uniform motion, such as the varying speed of the moon along its orbit. This feature aligns with Greek astronomical theories that accounted for irregularities through geometric constructs. The presence of such mechanisms raises important questions about the technological capabilities of the ancient world. Were devices like the Antikythera mechanism unique, or were they part of a broader tradition now largely lost? The surviving evidence is limited, but ancient texts provide hints that complex machinery was not entirely unknown. Writings attributed to Archimedes, for example, describe mechanical models of the heavens. Later authors, including Cicero, mention devices that could simulate the motions of celestial bodies. Cicero, in his work De Republica, refers to a sphere constructed by Archimedes that demonstrated the movements of the sun, moon, and planets. While the exact nature of these devices remains uncertain, they suggest that the conceptual foundation for the Antikythera mechanism was not isolated. Nevertheless, the physical survival of such intricate machinery is exceedingly rare. Bronze was a valuable material, often melted down and reused, leaving little trace of technological artifacts. The Antikythera mechanism may represent a class of instruments that were more common in antiquity than the archaeological record currently indicates. The shipwreck in which it was found provides additional context. The vessel appears to have been transporting luxury goods, possibly from the eastern Mediterranean toward Rome. This was a period when Roman elites were increasingly drawn to Greek art, science, and culture. It is possible that the mechanism was intended as a high-status object, valued not only for its practical function but also as a demonstration of intellectual and technical achievement. The craftsmanship required to produce the device suggests the involvement of highly skilled artisans working in collaboration with knowledgeable scholars. The integration of theoretical astronomy with mechanical design would have required both mathematical insight and precision engineering. This combination points to centers of learning such as Rhodes or Alexandria, where scientific inquiry and technical expertise were closely linked. Rhodes, in particular, has been proposed as a possible origin for the mechanism. The island was known for its tradition of astronomy and engineering, and for figures such as Posidonius, a philosopher and scientist whose work influenced later Roman thought. Some scholars argue that the intellectual environment of Rhodes could have supported the development of such a device, though definitive evidence remains elusive. As research into the Antikythera mechanism has progressed, modern technology has played a crucial role. Advanced imaging techniques, including computed tomography, have allowed researchers to examine the internal structure of the fragments without damaging them. These methods have revealed previously hidden gears and inscriptions, significantly enhancing understanding of the device's function. The inscriptions themselves are of particular importance. Written in Greek, they provide detailed information about the mechanism's operation and the astronomical phenomena it represents. The language and style of the text have been used to approximate the date of construction, generally placing it in the late 2nd or early 1st century BC. This aligns with the dating of the shipwreck, suggesting that the device was relatively new at the time of its loss. Despite these advances, many aspects of the mechanism remain subjects of scholarly debate. The exact configuration of some components is uncertain, and interpretations of certain inscriptions vary. Questions also persist regarding the extent of its capabilities, whether it modeled all 5 known planets, for example, or focused primarily on the Sun and Moon. What is clear, however, is that the Antikythera mechanism represents a level of technological sophistication that challenges earlier assumptions about ancient science. It demonstrates that the theoretical achievements of Hellenistic astronomy were not confined to abstract texts, but could be embodied in complex, functional devices. This realization invites a broader reconsideration of the transmission and loss of knowledge in antiquity. The mechanism stands as a rare, tangible link to a tradition that may have been more extensive than surviving evidence suggests. Its rediscovery has prompted historians to re-examine ancient sources with renewed attention, searching for overlooked references to similar technologies. At the same time, it highlights the fragility of technological heritage. The survival of the Antikythera mechanism was largely accidental, preserved by the conditions of the seabed. Without this chance discovery, the existence of such devices might have remained entirely unknown. As the fragments continue to be studied, they offer not only insights into ancient engineering, but also into the intellectual ambitions of a society that sought to understand and represent the cosmos through both theory and craft. The mechanism is not merely an artifact. It is a testament to a moment in history when knowledge, observation, and ingenuity converged in a form that still commands attention more than 2 millennia later. The Antikythera mechanism, once recognized as a device of extraordinary complexity, invites closer examination of its internal structure and operational design. Each surviving fragment, though corroded and incomplete, contributes to a larger reconstruction of how the mechanism functioned and what it reveals about ancient scientific practice. Through decades of careful analysis, scholars have pieced together a model that illustrates not only the ingenuity of its makers, but also the depth of astronomical knowledge it encodes. At its core, the mechanism consisted of a series of bronze gears mounted within a rectangular wooden case, roughly the size of a small shoebox. The front and back of the case were fitted with dials, each inscribed with scales and explanatory text. A hand-operated crank, likely attached to the side, would have set the internal gear system in motion. As the user turned the crank, the gears rotated in coordinated sequences, driving pointers across the dials to display astronomical information. The front dial is generally understood to have represented the movements of the Sun and the Moon against the backdrop of the zodiac. The zodiac itself, a division of the sky into 12 equal parts, was a standard framework in Hellenistic astronomy, inherited from earlier Babylonian traditions and adapted into Greek scientific thought. Around the perimeter of the dial, inscriptions marked the 12 zodiac signs, while an inner ring may have represented the Egyptian calendar of 365 days. 2 pointers likely indicated the positions of the Sun and the Moon. The solar pointer would have moved at a uniform rate, reflecting the apparent annual motion of the Sun along the ecliptic. The lunar pointer, however, required a more sophisticated representation. The Moon does not move at a constant speed in the sky. Its motion varies due to the elliptical nature of its orbit. To account for this irregularity, the mechanism incorporated an epicyclic gear system. This epicyclic arrangement is one of the most technically impressive features of the device. It consists of a small gear mounted on a larger rotating gear, allowing for variations in angular velocity. As the system turns, the interaction between the gears produces a motion that approximates the observed changes in the moons. This design reflects the influence of geometric models developed by Greek astronomers, who used combinations of circles, deferents, and epicycles to describe celestial motion. In addition to indicating position, the lunar display likely included a mechanism for showing the phase of the Moon. Some reconstructions suggest the presence of a small sphere, half black and half white, rotating to represent the changing illumination of the lunar surface. This feature would have provided a visual representation of the lunar cycle, enhancing the device's practical and educational value. Turning to the back of the mechanism, the complexity becomes even more apparent. 2 large spiral dials dominate this side, each corresponding to a different astronomical cycle. The upper spiral is associated with the Metonic cycle, a period of 19 solar years that closely aligns with 235 lunar months. This cycle was widely used in ancient calendar systems to synchronize lunar and solar timekeeping. The Metonic dial is divided into 5 turns of a spiral, with each segment representing 1 lunar month. As the mechanism operated, a pointer would have moved along the spiral, indicating the current month within the 19-year cycle. Inscriptions alongside the scale likely named specific months and possibly indicated intercalary months, additional months inserted to maintain alignment between the lunar and solar calendars. Below the Metonic dial is another spiral, representing the Saros cycle. This cycle, lasting approximately 18 years and 11 days, governs the periodic recurrence of solar and lunar eclipses. Ancient astronomers had recognized that eclipses tend to repeat with similar characteristics after one Saros period, making it a valuable tool for prediction. The Saros dial is divided into 223 segments, each corresponding to a synodic month, the time between successive new moons. Within these segments, inscriptions identify the type of eclipse that may occur, along with additional details such as the time of day and the magnitude of the event. While the mechanism could not predict the precise geographic visibility of an eclipse, it provided a framework for anticipating when eclipses were likely to happen. Adjacent to the Saros dial is a smaller subsidiary dial, often interpreted as representing the exoligmos cycle. This cycle, equal to 3 Saros periods, accounts for the shift in time of day that occurs with each successive Saros. By incorporating the exoligmos, the mechanism could refine eclipse predictions, indicating not only when an eclipse might occur, but also whether it would be visible during daylight or nighttime hours. The integration of these cycles into a single mechanical system required careful calculation of gear ratios. Each gear pair translates rotational motion in a way that reflects a specific numerical relationship. For example, the ratio between gears driving the metonic cycle corresponds to the relationship between solar years and lunar months. Achieving this level of precision would have required both mathematical planning and practical experimentation. The inscriptions on the mechanism play a crucial role in understanding its function. Unlike many ancient artifacts, which rely on external texts for interpretation, the Antikythera Mechanism contains its own explanatory framework. The Greek text, though partially damaged, provides instructions for reading the dials and interpreting the results. It also includes descriptions of the astronomical phenomena represented, suggesting that the device was intended for users with some level of education in these subjects. Analysis of the lettering style and linguistic features has helped scholars approximate the date and origin of the mechanism. The script is consistent with forms used in the Hellenistic period, reinforcing the dating suggested by the shipwreck context. The content of the inscriptions further reflects a synthesis of Greek and Babylonian astronomical traditions, illustrating the cross-cultural exchange of knowledge that characterized this era. The question of planetary representation remains an area of ongoing research. Some scholars argue that the mechanism may have included displays for the 5 known planets: Mercury, Venus, Mars, Jupiter, and Saturn, each of which exhibits complex motion relative to the fixed stars. Modeling planetary motion would have required additional gears and more intricate arrangements, potentially beyond what is preserved in the surviving fragments. Evidence for planetary displays is suggestive but not conclusive. Certain fragments contain gear structures that do not clearly correspond to the known lunar or solar cycles, leading some researchers to propose that they served planetary functions. However, the incomplete nature of the mechanism makes definitive reconstruction challenging. As a result, interpretations vary, and the full extent of the device's capabilities remains a subject of scholarly debate. Beyond its technical features, the Antikythera Mechanism offers insight into the purposes it may have served. It is unlikely to have been a tool for routine observation, as its operation does not involve direct measurement of celestial bodies. Instead, it appears to have functioned as a predictive and educational instrument, translating complex astronomical theory into a tangible, interactive form. Such a device could have been used in a variety of contexts. In an academic setting, it may have served as a teaching tool, demonstrating the relationships between different cycles and the principles underlying Greek astronomy. In a more elite environment, it might have been valued as a symbol of intellectual sophistication, reflecting both scientific knowledge and technical mastery. The craftsmanship evident in the mechanism suggests that it was not a mass-produced object. Each gear had to be carefully cut and fitted, requiring specialized tools and considerable skill. This level of workmanship implies the existence of workshops capable of producing precision instruments, as well as a clientele willing to commission them. The broader technological context of the Hellenistic world supports this possibility. Advances in mathematics, engineering, and materials science had created an environment in which complex devices could be conceived and constructed. Water clocks, for example, had evolved into sophisticated instruments capable of measuring time with considerable accuracy. Automata, mechanical devices designed to mimic living beings, were described in texts and may have been built for entertainment or demonstration. Within this context, the Antikythera mechanism can be seen as part of a continuum of innovation. It represents a convergence of theoretical and practical knowledge, drawing on established traditions while pushing the boundaries of what could be achieved mechanically. Its existence suggests that the line between abstract science and applied technology was more fluid in antiquity than is sometimes assumed. At the same time, the rarity of such devices in the archaeological record raises important questions. Was the Antikythera mechanism an isolated experiment, or does it represent a lost tradition of mechanical computation? The absence of similar artifacts makes it difficult to answer definitively. However, the references in ancient literature to devices capable of modeling the heavens indicate that the underlying concepts were not unique. The preservation of the mechanism, fragmented though it is, provides a rare opportunity to explore these questions. Each new study adds to a growing body of knowledge, refining our understanding of how the device was constructed and used. Yet even as the details become clearer, the broader implications continue to unfold. The Antikythera mechanism stands at the intersection of science, technology, and culture. It embodies the intellectual ambitions of a society that sought to comprehend the cosmos through systematic observation and mathematical reasoning. At the same time, it reflects the practical skills required to translate those ideas into a working instrument. In examining its structure and function, one is confronted with a level of sophistication that challenges traditional narratives of technological progress. The mechanism does not fit easily into a linear model of development, in which complex machinery emerges gradually over time. Instead, it appears as a highly advanced creation within a historical context where such devices are otherwise scarcely documented. This apparent discontinuity invites further reflection on the processes by which knowledge is preserved, transmitted, and sometimes lost. The Antikythera mechanism, in its silent complexity, offers a glimpse into a world where scientific insight and mechanical ingenuity were combined in ways that remain only partially understood today. The existence of the Antikythera mechanism prompts a broader inquiry into the intellectual and technological traditions that made such a device possible. It did not emerge in isolation, nor can it be understood solely as an exceptional artifact detached from its historical context. Rather, it reflects a convergence of developments in astronomy, mathematics, craftsmanship, and cross-cultural knowledge exchange that characterized the Hellenistic world. By the 3rd and 2nd centuries BCE, the Eastern Mediterranean had become a network of interconnected centers of learning. Following the conquests of Alexander the Great, Greek language and scholarship spread across regions previously influenced by Egyptian, Persian, and Mesopotamian traditions. This period saw the establishment of institutions such as the Library of Alexandria, where scholars collected, studied, and synthesized knowledge from diverse sources. Astronomy, in particular, benefited from this exchange. Babylonian astronomers had, for centuries, recorded detailed observations of celestial phenomena, identifying regularities in the motions of the moon and planets. Their approach was largely arithmetic, focusing on numerical patterns and predictive schemes. Greek astronomers, by contrast, developed geometric models to explain these motions, seeking underlying principles that could account for observed irregularities. The Antikythera mechanism appears to embody a synthesis of these traditions. The cycles it encodes, such as the Metonic and Saros cycles, were known through Babylonian observation, yet their implementation within a system of gears reflects a distinctly Greek emphasis on geometric representation. This combination suggests that the designers of the mechanism were not only familiar with multiple strands of astronomical knowledge, but capable of integrating them into a coherent mechanical framework. Such integration required more than theoretical understanding. It depended on the availability of skilled artisans capable of translating abstract relationships into physical components. The precision of the gears, with their carefully shaped teeth and consistent spacing, indicates the use of advanced techniques in metalworking. While the exact tools employed are not fully documented, it is likely that craftsmen used files, chisels, and possibly early forms of lathes to achieve the necessary accuracy. The question of where this expertise was concentrated remains open to interpretation. Several locations have been proposed, each supported by different strands of evidence. Alexandria, as a major center of scholarship, is often considered a candidate. Its association with figures such as Archimedes and later engineers suggests an environment in which theoretical and practical knowledge could intersect. However, Rhodes presents an equally compelling possibility. Known in antiquity for its schools of philosophy and science, Rhodes was home to astronomers who contributed to the development of celestial models. The island also had a reputation for mechanical ingenuity. Some scholars have pointed to stylistic features of the inscriptions and the nature of the astronomical cycles as aligning with Rhodian traditions. Another possibility is that the mechanism was produced within a network of workshops rather than a single location. The Hellenistic world was characterized by mobility of scholars, artisans, and ideas. It is conceivable that knowledge circulated between centers, with different aspects of the mechanism's design reflecting contributions from multiple regions. Regardless of its precise origin, the Antikythera mechanism demonstrates that the capacity for complex mechanical construction existed in antiquity. This raises the question of why similar devices are not more widely preserved. The answer likely lies in a combination of material, economic, and historical factors. Bronze, the primary material of the mechanism, was both valuable and reusable. Objects made from it were often melted down and repurposed, particularly during periods of economic strain or political upheaval. This practice would have limited the survival of intricate devices, especially those not considered essential. In addition, the production of such mechanisms may have been limited to a small number of specialized workshops. If these workshops declined or disappeared, whether due to changing economic conditions, loss of patronage, or broader disruptions, the knowledge required to produce similar devices could have been diminished or lost. The transition from the Hellenistic period to Roman dominance also altered the intellectual landscape. While Roman society valued Greek learning, its priorities were often oriented toward practical engineering, roads, aqueducts, and military technology, rather than the development of theoretical models of the cosmos. This shift may have influenced the types of devices that were produced and preserved. Literary sources from the Roman period provide glimpses of earlier technological achievements, though often without detailed descriptions. References to mechanical spheres and astronomical models suggest that devices similar in concept to the Antikythera mechanism were known, at least among educated elites. However, the lack of surviving examples makes it difficult to assess their prevalence or sophistication. One of the most frequently cited accounts comes from Cicero, who describes a device attributed to Archimedes that could reproduce the motions of celestial bodies. Cicero's description emphasizes the ability of the device to demonstrate complex astronomical relationships through mechanical means. While it is not possible to determine whether this device resembled the Antikythera mechanism in structure, the conceptual similarity is notable. Other ancient authors, including Pappus and Proclus, refer to mechanical models used in astronomical study. These references indicate that the idea of representing celestial motion through machinery was not an isolated innovation. Instead, it formed part of a broader tradition in which scientific concepts were explored through both theoretical and practical means. Despite these textual references, the Antikythera mechanism remains unique in its level of preservation and detail. It provides a rare opportunity to examine the physical implementation of ideas that are otherwise known only through written descriptions. In doing so, it bridges a gap between abstract knowledge and tangible artifact. Modern efforts to reconstruct the mechanism have relied on a combination of imaging technology, experimental archaeology, and comparative analysis. By examining the surviving fragments and modeling their interactions, researchers have proposed various configurations that account for the observed gear ratios and inscriptions. These reconstructions, while necessarily provisional, offer insight into how the device may have operated in practice. One of the challenges in this process is the incomplete nature of the evidence. Many parts of the mechanism are missing, and those that remain are often fragmented or distorted by corrosion. As a result, reconstructions must be based on a combination of direct observation and informed inference. Different scholars may propose alternative arrangements, each supported by plausible reasoning but subject to revision as new data emerges. This process of reconstruction highlights the interpretive nature of historical inquiry. The Antikythera mechanism is not a fully preserved object that can be understood at a glance. It requires careful analysis, comparison with known principles, and a willingness to revise conclusions in light of new evidence. In this sense, it serves as both a subject of study and a case study in the methods of archaeology and history of science. The mechanism also invites reflection on the relationship between knowledge and its transmission. The sophistication of the device implies a body of expertise that extended beyond a single individual. It suggests the existence of teaching, apprenticeship, and possibly written manuals that guided its construction and use. Yet such supporting materials have not survived, leaving only the device itself as a witness to its tradition. This absence raises important questions about the durability of knowledge systems. The survival of ideas depends not only on their creation, but on their preservation and dissemination. In the case of the Antikythera mechanism, the underlying principles of astronomy continue to be studied and transmitted through texts. However, the specific techniques required to embody those principles in complex machinery appear to have been less enduring. It is possible that similar devices continue to be produced in limited contexts, but that their traces have not been preserved. Alternatively, the knowledge may have gradually faded as the conditions that supported it, economic resources, institutional frameworks, and skilled practitioners, changed over time. The Antikythera mechanism thus occupies a distinctive position in the history of technology. It is both a product of its time and an outlier within it. Its existence demonstrates that the boundaries of ancient engineering were broader than once assumed, while its rarity underscores the uneven survival of technological achievements. As research continues, the mechanism remains a focal point for interdisciplinary study. Historians, archaeologists, physicists, and engineers contribute to a collective effort to understand its design and significance. Each perspective adds depth to the interpretation, revealing new aspects of how the device functioned and what it represents. In this ongoing investigation, the Antikythera mechanism serves not only as an object of fascination, but as a reminder of the complexity of the past. It challenges simplified narratives and encourages a more nuanced appreciation of ancient knowledge. Through its gears and inscriptions, it offers a glimpse into a world where observation, calculation, and craftsmanship were brought together in a form that continues to invite careful and measured study. The Antikythera mechanism not only reflects the intellectual achievements of its time, but also raises enduring questions about the processes by which knowledge is preserved, adapted, and sometimes diminished across generations. Its apparent isolation in the archaeological record has encouraged scholars to look beyond the device itself and consider the broader historical transitions that shaped the fate of complex mechanical knowledge in the ancient world. During the late Hellenistic period, the Eastern Mediterranean remained a region of active intellectual exchange. Centers such as Alexandria, Pergamon, and Rhodes supported communities of scholars engaged in mathematics, astronomy, and engineering. Yet this environment was not static. Political changes, particularly the gradual consolidation of Roman authority, altered the structures that had previously sustained scientific inquiry. Roman engagement with Greek knowledge was significant but selective. Roman elites often valued Greek education, employing tutors and collecting texts, but the institutional frameworks that had supported sustained research, libraries, scholarly communities, and patronage networks, were not always maintained in the same form. In some cases, knowledge continued through adaptation. In others, it appears to have narrowed in scope. The Antikythera mechanism emerges from this transitional context. The shipwreck that preserved it likely occurred during a period when Greek artifacts, including works of art and scientific instruments, were being transported westward. This movement reflects a broader pattern in which Greek cultural and intellectual products were integrated into Roman society, often as symbols of refinement and status. Whether the mechanism was intended for practical use, educational demonstration, or as an object of prestige remains uncertain. Its complexity suggests that it required a knowledgeable user, someone capable of interpreting its dials and inscriptions. This implies a setting in which such knowledge was accessible, perhaps within a scholarly circle or among individuals with advanced education in astronomy. At the same time, the mechanism's design indicates a high level of specialization in its construction. The creation of interlocking gears with precise ratios required not only theoretical planning but also consistent craftsmanship. This combination suggests that the knowledge embodied in the device was distributed across different domains: mathematicians or astronomers who understood celestial cycles, and artisans who could translate those cycles into mechanical form. The continuity of such collaboration depended on stable conditions, economic support, institutional continuity, and the transmission of skills through apprenticeship or written instruction. When these conditions were disrupted, the survival of complex technologies could be affected. The historical record indicates that the centuries following the Hellenistic period were marked by significant changes, including shifts in political power, economic networks, and cultural priorities. It would be inaccurate to characterize this period as one of uniform decline. Scientific and technical knowledge continued to develop in various forms across different regions. However, the specific tradition represented by the Antikythera mechanism appears to have become less visible in the surviving material record. The reasons for this are not fully understood, but several factors have been proposed. One consideration is the role of materials. As with many bronze objects, mechanisms like this could be dismantled and recycled. Over time, this would reduce the likelihood of their preservation. Unlike stone or ceramic artifacts, which often survive in large quantities, metal objects are more susceptible to reuse and loss. Another factor is the nature of the knowledge itself. Mechanical computation, as embodied in the Antikythera mechanism, required a convergence of disciplines. If any one component of this system, astronomical theory, mathematical modeling, or precision craftsmanship, became less accessible or less valued, the overall tradition could diminish. The survival of texts alone would not necessarily preserve the practical techniques needed to construct such devices. In considering the transmission of knowledge, it is important to recognize the role of education and documentation. While many works of ancient science were preserved through copying and translation, others were lost. The survival of texts was often contingent on their perceived relevance to later audiences. Works that aligned with prevailing intellectual or religious frameworks were more likely to be retained, while others may have been neglected. Mechanical devices, unless accompanied by detailed descriptions, were particularly vulnerable. Without surviving manuals or diagrams, the knowledge required to reproduce them would have depended heavily on direct instruction. If such instruction ceased, the techniques could be difficult to reconstruct, even if the underlying principles remained known. Despite these challenges, elements of ancient scientific knowledge did persist and evolve. In the later Roman and Byzantine periods, as well as in the Islamic Golden Age, scholars continued to study astronomy, mathematics, and engineering. Translations of Greek texts into Syriac and Arabic played a crucial role in preserving and expanding this knowledge. Observatories were established, instruments refined, and new theories developed. Within these later traditions, there is evidence of mechanical ingenuity, including devices that measured time, tracked celestial motion, and automated certain functions. However, direct parallels to the Antikythera mechanism are rare. While some instruments, such as astrolabes, served related purposes in representing the heavens, their design and operation differed significantly from the geared system found in the mechanism. This distinction highlights the diversity of approaches to scientific representation. The Antikythera mechanism relied on a system of gears to encode mathematical relationships, effectively performing calculations through mechanical motion. Other traditions favored geometric or analog methods, using rotating plates, projections, or observational alignment to achieve similar ends. The absence of direct continuity does not necessarily imply complete loss. It may reflect shifts in preference, practicality, or conceptual framework. Different cultures and periods emphasize different tools, shaped by available materials, prevailing theories, and specific needs. The Antikythera mechanism represents one approach among many, distinguished by its particular combination of precision and integration. Modern study of the mechanism has also prompted reflection on the nature of technological progress. It challenges the assumption that complexity increases steadily over time, suggesting instead that knowledge can emerge, flourish, and reseed in ways that are not strictly linear. The device demonstrates that high levels of sophistication can exist in contexts where they are not widely documented or preserved. This perspective encourages a more nuanced understanding of the past, one that recognizes both the achievements and the limitations of historical evidence. The Antikythera mechanism is not simply an anomaly, it is a reminder that the archaeological record is incomplete, shaped by chance, preservation conditions, and patterns of human activity. In recent decades, continued investigation of the shipwreck site has yielded additional fragments and artifacts, contributing to a more comprehensive picture of the context in which the mechanism was found. Advances in underwater archaeology have allowed for more systematic exploration, revealing details about the ship's construction, cargo, and route. These findings help situate the mechanism within a broader network of trade and cultural exchange. At the same time, technological advances in imaging and analysis have deepened understanding of the fragments themselves. High-resolution scanning has made it possible to detect faint inscriptions and subtle structural features that were previously obscured. Digital modeling has enabled researchers to test different reconstructions, evaluating how various configurations would have functioned. These methods have not only clarified aspects of the mechanism's design, but also underscored the collaborative nature of its study. No single discipline can fully account for its complexity. Historians provide context, linguists interpret inscriptions, engineers analyze mechanical feasibility, and astronomers assess the accuracy of the encoded cycles. Together, these perspectives contribute to an evolving interpretation that remains open to refinement. The Antikythera mechanism thus continues to serve as a focal point for inquiry, not only into ancient technology but into the broader dynamics of knowledge itself. It invites consideration of how ideas are translated into material form, how skills are transmitted across generations, and how cultural and historical changes influence what is preserved or forgotten. In examining its legacy, it is important to avoid projecting modern expectations onto the past. The mechanism does not imply that ancient societies were uniformly equipped with advanced machinery, nor does it suggest a hidden technological trajectory parallel to later developments. Rather, it illustrates the capacity for innovation within specific contexts, shaped by particular combinations of knowledge, resources, and purpose. As the fragments remain under study, they continue to offer insights into a moment in history when the desire to understand the cosmos found expression in an object of remarkable intricacy. The Antikythera mechanism stands as both a testament to human ingenuity and a prompt for continued exploration, an artifact that, even in its incomplete state, encourages careful and measured reflection on the nature of ancient knowledge and its enduring significance. The continuing study of the Antikythera mechanism has not only clarified aspects of its structure and purpose, but has also prompted a broader reassessment of how ancient scientific knowledge is interpreted in the modern era. As new imaging technologies and analytical methods have revealed previously hidden details, the device has become a focal point for interdisciplinary research, drawing together expertise from fields that rarely converge so directly. One of the most significant developments in recent decades has been the use of high-resolution computed tomography to examine the internal structure of the surviving fragments. These scans have allowed researchers to visualize layers of gears, inscriptions, and structural components without physically altering the artifact. Through this process, details that were once obscured by corrosion have become legible, including fine lettering and subtle variations in gear design. The inscriptions, in particular, have proven to be a rich source of information. Numbering in the thousands of characters, they represent one of the most extensive surviving technical texts from the ancient Greek world embedded within a physical object. Their content includes instructions for operating the mechanism, descriptions of the astronomical cycles represented, and explanatory notes that guide interpretation. The language of these inscriptions reflects a practical orientation. Rather than presenting abstract theory, they provide operational context, indicating what a user would see on each dial, how to interpret eclipse predictions, and how different cycles relate to one another. This suggests that the mechanism was designed not merely as a conceptual model, but as an instrument intended for use. At the same time, the level of detail implies a user with some degree of prior knowledge. The inscriptions assume familiarity with terms related to the zodiac, lunar phases, and calendrical systems. This reinforces the idea that the device functioned within an educated environment, possibly among scholars, teachers, or individuals engaged in astronomical study. Modern reconstructions of the mechanism, based on the cumulative findings of imaging and analysis, have attempted to recreate its original appearance and operation. These reconstructions vary in certain details, reflecting ongoing debates about specific components, but they share a general framework: a compact, gear-driven instrument capable of modeling multiple astronomical cycles simultaneously. Experimental versions built by researchers and engineers have demonstrated that such a device is mechanically feasible using ancient techniques. By replicating the gear ratios and arrangements identified in the fragments, these models produce motions that align closely with known astronomical cycles. This practical validation reinforces the interpretation that the original mechanism functioned as intended, rather than representing an incomplete or purely theoretical construct. Yet even as these reconstructions bring the mechanism closer to comprehension, they also highlight the limits of current knowledge. Certain features remain uncertain, including the exact configuration of missing gears and the full extent of the device's capabilities. The possibility of planetary displays, for example, continues to be explored, with some models incorporating additional gear trains to simulate the motions of Mercury, Venus, Mars, Jupiter, and Saturn. However, the fragmentary evidence leaves room for differing interpretations. These uncertainties are not obstacles to understanding, but integral aspects of the investigative process. They reflect the nature of historical evidence, which often requires interpretation rather than direct observation. The Antikythera mechanism, in this sense, serves as a reminder that knowledge of the past is constructed through a combination of data, inference, and critical evaluation. Beyond its technical features, the mechanism has influenced broader discussions about the history of science and technology. It has prompted historians to reconsider assumptions about the capabilities of ancient societies, particularly in relation to mechanical engineering. While it does not imply that such devices were widespread, it demonstrates that the conceptual and practical foundations for complex machinery were present. This realization has encouraged renewed attention to ancient texts that describe mechanical devices. In some cases, passages that were once considered exaggerated or ambiguous are now revisited with greater appreciation for their potential accuracy. References to automata, water-driven mechanisms, and astronomical models are examined in light of the Antikythera evidence, suggesting that the technological landscape of antiquity may have been more varied than previously assumed. At the same time, scholars emphasize the importance of maintaining a balanced perspective. The Antikythera mechanism is an extraordinary artifact, but it should not be used to generalize about all aspects of ancient technology. Its uniqueness underscores both the achievements and the limitations of the period in which it was created. It represents a peak within a specific domain, rather than a baseline for the entire society. The mechanism also contributes to discussions about the relationship between science and craftsmanship. In modern contexts, these domains are often treated as distinct, with clear boundaries between theoretical research and practical application. In the Hellenistic world, however, the distinction appears to have been more fluid. The creation of the Antikythera mechanism required collaboration between individuals with different forms of expertise, suggesting an environment in which knowledge was shared across disciplinary lines. This integration is reflected in the device itself. The gears encode mathematical relationships derived from astronomical observation, while their physical arrangement embodies principles of mechanical design. The result is an object that operates at the intersection of theory and practice, translating abstract concepts into tangible motion. The study of such an object also invites reflection on the nature of innovation. The Antikythera mechanism did not emerge from a single moment of invention, but from a cumulative process in which ideas were developed, refined, and combined over time. Its design incorporates cycles known for centuries, mathematical techniques developed by successive generations, and craftsmanship honed through practical experience. Understanding this process helps to situate the mechanism within a broader historical narrative. It is not an isolated anomaly, but part of a continuum of inquiry and experimentation. Its apparent singularity in the archaeological record may reflect the selective survival of evidence rather than the uniqueness of the underlying tradition. In recent years, the Antikythera mechanism has also become a subject of public interest, featured in exhibitions, documentaries, and educational materials. This visibility has contributed to a wider appreciation of ancient science, while also presenting challenges in communication. Simplified or sensational interpretations can obscure the careful, evidence-based conclusions reached by researchers. As a result, scholars often emphasize the importance of distinguishing between established findings and areas of ongoing debate. While certain aspects of the mechanism, such as its use of the Metonic and Saros cycles, are well supported by evidence, others remain provisional. Maintaining this distinction is essential to preserving the integrity of the historical interpretation. The mechanism's legacy extends beyond its immediate historical context. It has influenced modern perspectives on the origins of computation, serving as an early example of a device that performs calculations through mechanical means. While it differs fundamentally from later digital computers, its ability to model complex systems through interconnected components reflects a shared conceptual foundation. This connection has inspired comparisons with later developments in clockwork, astronomical instruments, and calculating machines. Medieval astronomical clocks, for example, incorporate gears to represent celestial motion, echoing principles seen in the Antikythera mechanism. However, these later devices emerged in different contexts, shaped by distinct technological and cultural influences. The Antikythera mechanism thus occupies a unique position within the long history of scientific instrumentation. It stands at an early point in the use of gears to represent abstract relationships, demonstrating a level of integration that would not become widely documented again for many centuries. As research continues, the mechanism remains an evolving subject of study. New findings, whether from the analysis of existing fragments or from further exploration of the shipwreck site, have the potential to refine current understanding. Each discovery contributes to a more detailed picture of how the device was constructed, how it functioned, and how it fits within the broader history of science. In this ongoing process, the Antikythera mechanism serves as both an object of inquiry and a source of insight. It reveals the depth of ancient knowledge while also illustrating the challenges of reconstructing that knowledge from incomplete evidence. Through careful study, it continues to inform not only what is known about the past, but how that knowledge is approached, interpreted, and understood.